Hello everyone, welcome back. My name is Renuka, Assistant Professor in Department of Electronics and Communication, Maharaja Institute of Technology, Mysore. Previous class we have studied about what do you mean by adaptive control, correct? So what is adaptive control? What are the different types of adaptive control? Do you remember? It was a pre-programmed controller, correct? Then you have self-tuning controller, and the third one was model reference controller, correct? So in previous class we have already dealt with what is meant by a pre-programmed controller, okay? So today we are going to study or focus main on what do you mean by self-tuned controllers, and what do you mean by model reference controllers, and what are the supervisory controllers, why is it required, and what is the advantages, and then about the multiple processors in a single computer, how efficient it could be. So these are some of the topics that you are going to study in today's class. To self-tuning adaptive control, identification technique to achieve continual determination of parameters of the process being controlled. So for example, if you remember, we had given an example regarding the crude oil extract, right? So what is happening there? It is a continuous system, okay? Continuous system, it is not a batch system, it is a continuous system, and there should be monitoring of the crude oil, its the extracts, right? And then it's later you have batch processing. After continuous you have batch processing to get the fractionates from the crude oil, correct? So now if you consider for a continual process, if you want to actually monitor the variation happening in a plant without disturbing the operation of a plant, what is that required? You need to have what is called as a parameter estimator, okay? So here in this block diagram, what can you see? You have set points. Set points is nothing but it could be temperature, it could be pressure, okay? These are few examples, or the velocity, the n number of physical parameters that could be taken as a set point here, which is very crucial for a plant, right? Based on this set points, you are going to operate the output. The controller has to operate in a system, right? So now the set points are connected to a controller, and these set points, how do you get it? From the controller output. So if there are any variations here, it will be sent back to the input at the set point. And now another variation parameter, so the adjustment, whatever you have to adjust with the variation that has been predicted from this controller, has to be done by the parameter estimator and the parameter adjustment, then connected to a controller. From the controller, it runs to the processor, and the processor takes up the controlling action. For example, let us take if during the time constraint in any of the operation, if a valve has to be open for say about in 5 seconds, within 5 seconds the valve has to be open, right? But what happens due to some erroneous operation here, the valve, the control output here might display, because there is a monitoring system too, right? It might say that the valve will be open in another 4 seconds. So what is happening? The valve is opening 1 second early, right? But that is not correct. What we want 5 seconds, but you are getting at 4 seconds, right? So now for that 1 second of correction has to be dealt. So this 1 second will be fed to the set point. So 1 second, so this is the output here, right? So output, what is estimated is 5 seconds, but you are getting for 4 seconds. So this variable is sent, the way the parameter estimator is done here. The estimation parameter that needs to be adjusted, okay, from 4 to 5 has to be rectified here at the parameter adjustment of the variable. Then it should be fed to the controller, right? Once it is fed to the controller, then processor, what will it do? It will try to check the estimated output to that of the corrected output. If it is correct, if both are equal, then that end result will be going through the controller output, okay? So then this controller now will not be running at 4 seconds, which was 1 second earlier or prior. it will run exactly, or it will make the valve open exactly at 5 seconds. Got it? So this is how actually it is called as a self-tuning, and nobody actually does it manually. Okay, it happens automatically. It gets adjusted within the system. For any variation in the process, during a continual process, if there is any variation, that adjustment happens within the control system. So that's why it's called as self-tuning adaptive control. It adapts to the variation at the output of the controller. Okay, it is similar to the previous block diagram. Here what do you have? You have again a set point, you have a controller, you have a processor, then you have a control output. Here you have what is called as adaptation mechanism, and you have disturbance. Okay, then you have reference model and you have disturbance. Now if you just look into it, model reference adaptive control, the only change is this mainly focuses on the disturbance caused by the external environment. Okay, so there is a reference set. Okay, so where if there is a reference set, okay, there is a reference for which the system has to be adapted. So for example, if there is if you take an example of air traffic control, okay, what happens during taking off or when the plane is propagating along a distance, what will happen? There might be 3 important criteria that you have to look into. One is the velocity of the air, okay, then the speed, okay, the temperature as well as the pressure. So temperature, pressure as well as the velocity, all these becomes an critical parameters for the entire plant. I can say the the aeroplane itself. Okay, so whatever disturbance happens externally, okay, that has to be that should not affect the plant or the system internally, correct? So that's here the block diagram is the self-tuning. This self-tuning happens during the process when the plant is running continuously. There is no stop or start in the process. Okay, but in case of this, wherein if there is any disturbance which leads to external disturbance affecting the plant, then it tunes or it adapts automatically. This also comes under the self-tuning adaptive control. Okay, the only difference here is you have a reference model, then you have a adaptation mechanism. Okay, and usually when you set a model, you say, for example, if I take students, okay, students come to college, they go, they learn all the courses in that particular semester, and will you just leave the college? No, you have to be tested, correct? You have to be tested for whatever you have learned, right? So if that is called as a self-tuning now, got it? So there is set marks allocation will be done. Okay, for example, if I take 10 marks out of 10, how much have you understood? If it is 10 of 10, then it's great. If not, what will happen? You are coming toward nearer to 10, so about 8, 8.5, 9, 9.5. You're closing, you're getting closer to the mark. Mark is what? The mark is the reference, right? So if you have a control system that is designed mainly to actually become a reference, okay, so reference based on which the entire plant is run, then you call it as a model reference adaptive control. So it relies on the ability to construct a model of the process, measure the disturbance which affect the process. So it will measure whatever the difference happens in the process and even externally for internal as well as external, and then you're setting up that as a model. So even for example, if I say I have ISI standards for any system to be upgraded or compared with, so those are the norms. So those are the reference, correct? Reference measurement for which you're going to calibrate any of the instruments, right? If it has gone bad, you have a reference standard for which it will be compared to. So there has to be certain reference set. So if a plant works as a reference model, then you call it as model reference adaptive. So automatically a plant will generate a fault by itself trying to validate its correctness. Are you able to understand? So now what will happen, as and when you keep giving exams, you face the exams, and you get 100 out of 100 for all the exams. Okay, so now there can be twisted question to calibrate yourself. Okay, we usually do that, right? We calibrate ourselves. So we'll try to create a problem, create some kind of an error within the system to gauge whether we are doing it correctly or not. There might be n number of ways, but it could be a right way to approach. Then if you are able to get that 100%, then you say that the reference model is perfect. So it is generating an error within the plant to gauge its performance. Okay, that is called as model reference adaptive control. I hope you are clear with self-tuning adaptive. And then you have one is mainly for the continuous process within and the external disturbance. Other is called as a reference model adaptive control, where you are going to set an error by the process itself to gauge its performance. Next, before getting into what is meant by PIDs and what actually supervisory control does, we have to just know what do you mean by PID. P is proportional integral derivative. So if you consider M of t is nothing but the message out. Okay, so now if that is an information, then you have Kp and you have E of t plus 1 by Ti integral 0 to t E of t dt plus Td differentiation of error E of t by dt. So this is the expression. Okay, this is the expression for your PIDs. Okay, so they are nothing but control algorithms which are mainly used. Okay, because you have to have complex algorithms for any of the control systems to work, correct? Because if you are getting into supervisory control, then you have computers. So if there are computers, there then have to be programming. If there is programming, obviously you have to work on the algorithm part. So this is a complex algorithm. So what does this E of t represent here? They are nothing but the measured variable. C of t is the measure variable, R of t is the reference variable of the set point, and E of t is the error. So if I consider, for example, you have a system, okay, you have a system here, okay, and they have an output, okay, and you have an input, okay, if this is a system, fine. So what happens if there is a feedback, okay, okay, there could be small amount of error. Okay, if I consider this, okay, this system again can have a small error E of t. So now I have to calculate what is this E of t. So E of t is mainly based on what is your R of t. R of t is nothing but the output of your the system, and then when it is fed back to the input, okay, then you have C of t. So it is measured, the error is nothing but the measured variable minus, okay, the reference value of the set point. So E of t is the error, okay, measured value to that of the reference value. So if you just take the difference between the two, the reference is, if it is 10 and the measured value is say about 4, then the error will be 6, 10 minus 6, so it becomes 6, right? So that 6 is an error, and that error has to be rectified in any of the system. How do you do that? By writing or integrating that error with respect to time, and reducing as to 0. So integration will always help in reducing the value to 0, and differentiation will always help to differentiate and set the level of the performance of the controller. Okay, so here Kp is nothing but the overall controller gain. So here what you see is Kp, and this Kp is mainly dependent on what is the output by the input. So output controller divided by the input errors. Okay, if I say that Kp here is nothing but the controller output by the error Okay. So just if you just see into this, look into it, if the constant is high, what will happen? The error is low, correct? So the lesser the error, the value of Kp, the constant, the controller constant will be more. So if the error is more, what will happen to Kp? Kp will be reduced. So I have to make sure that Kp is always higher so that the error is low in a plant. Okay, so that could be rectified. So Kp is nothing but the overall controller gain, which can be modified based on the controller output and the controller output. So you have Ti, which is nothing but here you have Ti, right, 1 by Ti. So it is the integral action time. So integral action time wherein the error will be integrated from 0 to T. Then you have integral operation leads to reduced steady state error to 0. So if there is any error, which is a known error in a plant, then you are reducing or integrating it. The name itself says it is integrated to value 0 or it is eliminated. So value of Ti plays a vital role here. Okay. Then if there is any sudden disturbance in a plant, okay, a control signal that is related to a rate of change of errors, that will reduce the error. So what happens here? You have d of, it is written as dE of T by dt, correct? So this differentiation here, okay, what you see is nothing but mainly to reduce the error, and this disturbance is caused by the external environment. So differentiating the same error which occurs from the outside. So here internal, we have external, right? So integrating the internal process error to that of differentiating the error caused by the external environment. So doing that, what will happen? You are trying to reduce the value of the error. So if you are reducing the value of the error, then the controller action will be very quick. The lesser the value of error, quicker is the operation. If quicker is the operation, then you have a greater performance. Okay. Now, keeping all those information in mind, okay, what is PID? So the advantage of this PID is they cope adequately to about 90% of all control problem. Okay. So it copes with all control problems related to a plant. So its adaptation is new control system design technique. So it will always be, it can adapt itself for any of the new plant or design techniques that you are going to use. So if you have that expression, try to understand what are the what is the probable errors, a steady state error in a plant. Try to integrate with reference to the time and differentiate the disturbance. Okay. Then the error that is set by external factor. If you do that, what will happen? You can always work on M of T. Okay. If M of T is defined well, the performance of the system or the plant will be good. Coming up to supervisory controller. Okay. What is the supervisory controller? We have already dealt from, in RTS, real-time operating systems, we usually started with a simple monitoring system, and then we have a supervisory system, right? So switches and dial replaced to VDUs and keyboards. So earlier when there was evolution in RTS, then you had lot of analog systems. In this analog system, you had lot of switches, okay, and lot of other keys that were used. But now what has happened, when it is partially digitized, what happens? Though you are using analog, there will be controllers used by a digital setup, right? So those analog systems were now mainly converted to VDUs, that is a visual display units, and keyboards. So doing that, the complexity of the system also increases, isn't it? So that's the reason supervisory controller is used than the DDC, that is a direct digital controller. Computers in the early days were not always very reliable, and caution detected that the plant should still be able to run even if the event in the computer fails. What do you mean by that? So it's simply saying that even if you have a computer which controls in an analog system, Okay, if you remember in the second class that we had dealt, that you have one computer which tries to monitor and lets the control system, okay, which controls the entire plant. The opening and closing of valve was controlled, isn't it? So that was not reliable, okay, because it also says that whenever the computer goes wrong, which is not able to detect, okay, the problems happening in the plant, what will happen? Then the entire plant will not be a failure. It will be only the computer that will fail, okay. The computer will fail, but the entire plant will be intact, okay. But to overcome this problem, because the second point it says that the computers were very expensive, because when you had analog computers with the digital softwares, it was very difficult even if you just let down with the entire software programs. If there is a failure in a system or a computer, to get back the hardware, okay, compatible to that of software was tedious and more expensive because of the limitations, right? But now it's not that. Now it can be replaced. Now you have standalone system, okay. If one operation fails, automatically it switch over to another processor, okay. So the best example to understand the supervisory control, if you just see here, in this block diagram, the supervisory control, as I just explained to you, you have a processor, you have all the actuators. Here A represents the actuators, okay, the process inputs, and you have process output. What C represent here is nothing but the control units, the control lines which are connected to the actuators. If I take this as valve 1, valve 2 and valve 3, they are all controlled by these C1, C2 and C3, okay, and this can be a computer by itself or a control line which will be again monitored by either human or by computer operations. So it can be auto or it could be manual, okay. So this was a set as a control, even if there is a system which collapses, but the plant will remain intact. But to get back the system working, it would be more expensive, okay. So the best way to explain that supervisory control is one of the evaporation plant that you can see here in the diagram. So in this evaporation plant, you have evaporation chambers here 1 and 2, okay. So here the main purpose of this plant is to make sure the water present in any liquid gets evaporated. So you just left with the residues, okay. Evaporation of the water present in a liquid, okay. Suppose if I consider an oil has its own melting point, boiling point, evaporation, correct? The same way the solution, the water present in the oil also varies, right? It also heats up in a different temperature, and it also requires different pressure, correct? So all these are kept in mind. So in this evaporation chamber, it tries to evaporate water present in any liquid, okay. The first chamber and the second chamber, they will be fed with materials, okay. Supply materials will be fed through these valves, okay. What you see, the dotted lines here indicates the level of liquid present, okay, along with water. Now what is a supervisory, who should supervise what? So in this kind of a plant, pressure plays a vital or a critical parameter or a variable which needs to be supervised, because if you are letting steam supply to the first chamber, okay, there will be sufficient amount of steam that is fed in to the first chamber, and high amount of pressure is exerted so that the evaporation happens at a greater extent in the first chamber. And if you just see, there is an outlet from the first chamber to the second. So whatever the pressure that is applied here, all this evaporated steam will go through the second chamber, and hence what happens, the pressure exerted here in the second chamber mainly depends on the first. The greater the pressure here, double the pressure it becomes over in the second chamber, right? So the pressure has to be monitored or maintained or balanced between the two chambers optimally, so that the overall outcome is the evaporation of the water, present in that liquid, right? So it says that two evaporators are connected in parallel and materials are being fed as seen here. Evaporation of water is using a very high pressure. So the steam supplied to the first and the vaporized steam to the second. So there are two. So the first you will be feeding it, here automatically the steam is fed to the second chamber. So balancing the steam pressure to maintain the overall evaporation rate. So we have to balance the evaporation rate of the liquid. So to increase the profitability, the complex algorithm and a non-linear model real-time operation in parallel with the plant operation. So what does it mean? So this is a crucial aspect where the pressure plays a vital role in this kind of a plant. Okay, if the pressure exerted is too very high in the first chamber, then you have to have a supervisor who can actually control. So letting in the steam and lowering it is under the control of the supervisor, correct? So the supervisor will make sure that both the plants have a optimal pressure here, right? So this is a straightforward and a very simple control system, but it will not be always simple, right? It can become more complex when you're going for different kinds of applications, okay, real-time applications. So as and when you go for a complexity, then the real-time control system also, the algorithm becomes more complex, right? It will not be linear anymore, it will become non-linear. So non-linear, adaptive, and it can also have, most complex algorithms that needs to be written and to be addressed. So these are some of the important aspects of the sequential or the supervisory control system. Let us just get into what do you mean by centralized computer control. So now centralized, so if I say that for example, if you take the college, okay, I call a principal chamber as a centralized control, okay, and head of the department. So each department, okay, has a head, correct? They become the supervisory control. So you have a centralized system, right? Centralized computers here means the principal there in an example, right? So whatever he or she says, that needs to be followed by the head of the department. So the head of the department will then deliver the same information that needs to be done to the next cadre, that is the faculty, the professors, right? So now what happens, there will be a central head, unlike if a country. So president becomes the central head, prime minister, he'll become the main action, he is a person who will be, okay, the president is centralized, if I consider him as a centralized computer. So what he does it, he will pass the bill, he will execute, he will take some important decisions, right? And the prime minister, what he says, he works, he makes sure all the chief ministers in the states, they work for the country, for the development of the country, correct? So now if you have one single centralized computer, just one computer, it is very difficult to make sure that all operations are maintained accurately, right? So if you have multiple such systems, as you see in the block diagram here, you have computer A and you have computer B, okay? So you have plant interfacing, then you're switching, control station. So if there is any failure in computer A, so the plant will not shut down. What will happen? You can have computer B as a standalone, which could operate in the absence of computer A, right? So which will not affect the plant productivity. So that's the reason we need to have a centralized computer control, or you can call it as a simple dual computer scheme. So digital control with an analog backup, which means signals were passed through the analog computer control to actuators by digital control signals, and they were very cost was very high, as both controllers were to be installed. And then dual computers, it would be manual change It can be even manual or it could be automatic. So the disadvantages of the supervisory control can be saying that cabling and interfacing not duplicated. It is very difficult to duplicate or get the hardware for a software or software to the hardware. Okay, compatibility so becomes very critical. So designing, programming, testing and maintaining software are not reduced. So these are some of the drawbacks of your supervisory control system, for which we have what is called as a dual scheme, wherein even if one fails, we have another as a standby, and this is how we can overcome such issues in a supervisory control. I hope you have understood the class. Thank you for listening.